Okay, so now I'm doing example 2. Now what I'm going to do is I'm going to find the eigenvectors. So I already have eigenvalues. So try to find the eigenvalues for example 2. The matrix A is -5, -3, -3, 3, 1, 3. Try to find the eigenvalues by yourself, but if you want to learn how to do that, you can refer my previous optional video. Okay, so the work is here. Alright, so the eigenvalues what I got is 4, and the other eigenvalue is repeated eigenvalue -2 repeated twice. So let's find the eigenvectors here. So we are still in special case 1. Okay. Alright, so let's use the non-repeated eigenvalue first. So you want to solve the equation a minus 4i, 4 is the eigenvalue, times k is equal to 0. So let's form this a minus 4i matrix. So you subtract 4 from the diagonal of a, right? Because 4 minus a minus 4i. So -5 minus 4 is -9, here -3, -3, 3, 1 minus 4 is -3, 3, 6, 6, 4 minus 4 is 0. So this is a minus 4i matrix. Now you want to solve for little case. Okay. Now we use Gaussian elimination, as you know. So let's write down the augmented matrix. So 3, -3, 3, 6, 6, 0. Now take a look at this matrix and decide what would you do first. Now you can see all the numbers are big, right? So, and if you further notice that all the numbers are multiplied by 3, or you can pull out a 3 from here, right? So let's divide the whole matrix by 3 just to make it simple. So this will be -3, -1, -1, 1, -1, 1, 2, 2, 0. Right, 0 divided by 3 is 0. So this is a much simpler version of the same augmented matrix, right? And you can perfectly do that. Okay, all right. Now here, look at the first pivot position. It's -3. Now it's non-zero, which is good, but the ideal pivot position will be 1. Can I trade these 2 rows and get 1 here? Yes, because I have 1 here, I will switch row 1 and row 2 just to get 1 here, and that makes our life very easy. At least we can avoid fractions. Okay, the fractions in a Gaussian elimination is usually cause up a mess. Okay, now I want to create 0 and 0 in those positions. So what I do is first multiply the row 1 by 3 and add it to the second row, because 3 plus -3 is 0. And then at the same time I'll multiply the first row by -2 and add it to the third row, because -2 plus 2 is 0. So since we have seen Gaussian elimination several times now, we can do that in our mind very fast. But remember, we don't change the row 1. Now here you will get 0. So -3, right, because you multiply by 3. -3 plus -1. -3 plus -1 is -4. Here 3 plus -1 is 2. Okay. Now I multiply the first row by -2. So here this will be 0. -2 times -1 is 2. 2 plus 2 is here 4. -2 plus -2 times 1 is -2. -2 plus 0 is -2. Okay, so this is what I get. Now we move on to the second pivot position. So the second pivot position is +4, right? Now -4, my bad. Now do you want to change it to become 1? No, right? Why? Because the whole purpose is to make this 4 0, but you can just add second row and third row. You directly get 0 on the bottom, right? So why do we change that -4 to 1? So let's add the second row and third row. So see, it's really depends on our purpose. Okay, 2 plus -2, 0 here. So we are done with the Gaussian elimination because we don't care about this position anymore. All right, so let's write down the matrix equation out of this elimination. Oops, this is 1. Come on. 1, -1, 1, 0, -4, 2, 0, 0, 0. Now little case, k1, k2, k3, 0, 0, 0. Okay, good. Now let's write down the equations. Again, k1 minus k2 plus k3 is equal to 0. Negative 4k2 plus 2k3 is equal to 0. So we get two equations, right? Okay, this is an unrepeated eigenvalue. So now let's use the second relation, which is if I take this term to the right, 2k3 is equal to 4k2. So k3 is, if you divide by 2, 2k2. So what would be, so we can choose k2, right? Then we get k3. What would be a guess for k2? Let's choose 1 for k2. Then k3 will be 2, right? Pretty easy. Now if you use the first equation, k1 minus k2 is 1. K3 is 2 is equal to 0. So here k1 plus 1 is equal to 0. So that means k1 is negative 1. So this is the eigenvector for the eigenvalue 4. Okay. Alright. So that's done. Now we want to move on and find the eigenvalue for the repeated eigenvalue. The repeated eigenvalue is negative 2, and let me write down the matrix A here very quickly. Negative 5, negative 3, negative 3, 3, 1, 3, 6, 6, 4. So this is the matrix. So let me confirm. Yes. Now we want to find the eigenvector for this repeated eigenvalue. So what do we do? A minus lambda I. So A minus 2i. So that means A plus 2i, right? So that means you add 2 to the diagonal. So negative 5 plus 2 is negative 3, negative 3, negative 3. 3, 1 plus 2 is 3, 3. 6, 6, 4 plus 2 is 6. Okay, so this is A plus 2i matrix. Now here, now we want to find the little case. Don't be in a hurry. Okay, 0, 0, 0. Okay, so now let's use the Gaussian elimination. Okay, so negative 3, negative 3. Here really we don't need Gaussian elimination, but still I would do it because that is what we have been doing. Oh, now we want to do the augmented matrix. My bad. So okay, right. Now what is the first thing you can do? Just like before, if you look at this augmented matrix as a whole, you can see there's a common factor, which is 3. Let's divide the whole matrix by 3, because every term here, every number here in this augmented matrix is a multiple of 3. So if you divide by 3, what you get is negative 1, negative 1, negative 1, 1, 1, 1, 2, 2, 2. Okay? Alright. So then we look at the first pivot position, which is negative 1, which is okay. Negative 1, 1 doesn't matter. Okay, so let's create zeros here and here. So to create 0 on the second position, we can add the first row to the second row, because negative 1 plus 1 is 0. So then, and then also I will multiply the first row by 2 and add it to the third row, because negative 2 plus 2 is 0. So what I get is negative 1, negative 1, negative 1 here. First row doesn't change. Negative 1 plus 1 is 0. Negative 1 plus 1 is 0. Negative 1 plus 1 is 0. Negative 2 plus 2 is 0. Negative 2 plus 2 is 0. Negative 2 plus 2 is 0, right? Because we multiply the first row by 2, okay, before we add it to the third row, okay? So 2 times negative 1 is negative 2. Negative 2 plus 2 is 0. That is how I get 0s here and here. So see, one step of the Gaussian elimination, you are done, right? I think it seems to be like repeated case is easy, right? Okay, so let's write down the matrix equation. Negative 1, negative 1, negative 1, 0, 0, 0, 0, 0, 0. So we want to solve for little case. Okay, so the matrix equation, the k equation would be from here, negative k1 minus k2 minus k3 is equal to 0. So then negative k1, so here we only get one equation. So we cannot just choose k3 and get k2 and get k1. We have to make two choices, right? With a one choice, you can't get anything. So here k1, negative k1 is negative k2 plus k3 if we take these terms to the right. Okay, so that means k1 is negative k2 minus k3. So what I do here is, well, we don't know k3, it's a free variable. We don't know k2, it's a free variable. K1 is negative k2 minus k3. That's the relation. Now I decompose this as, what are the coefficients of k2? Negative 1 from here, 0, no, Here you have a k2, it's 1 here, here no k2. So that's the coefficients of k2. Coefficients of k3 here, -1, there's no k3 in the second row, there's a 1 k3 in the third row. So we get 2 linearly independent eigenvectors from here. So for eigenvalue -2, my eigenvectors are -1, 1, 0, comma -1, 0, 1. These two. Okay, so previously we found the eigenvector for lambda 1 is equal to 4 was -1, 1, 2. So we can write the general solution now. Okay, so let's write the general solution. The first C1 times -1, 1, 2 and e to the 4t is the corresponding eigenvalue plus C2. Here -1, 1, 0, e to the -2 is the corresponding eigenvalue plus C3. The other eigenvector is -1, 0, 1, e to the -2t. So we treat it like a distinct eigenvalue case, but we still have repeated eigenvalues, but we were able to find linearly independent eigenvectors. Okay, all right, that's it. Thank you.